supersymmetric field theories, but you already know that, I guess. So I'm not going to waste your time, and let us invite our speaker to introduce his.
Recording in progress.
Please.
Good afternoon, everybody. So I speak English, so probably some of you will prefer Russian, I don't know. But anyway, so we can speak both languages. So first of all, let me thank the organizers for invitation to give a talk. And let me give you all the warmest regards from Dubna, from the Laboratory of Theoretical Physics. So some of you probably have been there, some of you been there for long. But anyway, welcome, come again, stay with us. We're alive. And the COVID situation in Dubna is rather mild today. Anyway, so the topic of my talk today is rather theoretical. I will talk about renormalization operations, and there was practically no connection with today's experimental data, but I will give some motivation why I have chosen this topic today. So, you know, we have 65 years of our institute this year. So some celebration takes place in Dubna, and now we're here on occasion of Committee of Plenipotentiaries, which took place here in Sofia. Yesterday we have a great meeting with your president. So everything on very high level. So I'm pleased that Bulgaria is still one of the key players in Joint Institute for Nuclear Research. And so as I say, all theorists are welcome to come to laboratory to work with us. All right, so let me start with my talk. Я куда-то нажимаю, но не пойму куда. Это поинтер?
Да, вот так.
Нет, вроде это должна тоже работать.
Это форма?
Я не туда нажимал. Right, so in the title of my talk, there is a non-renormalizable theory. You may wonder why I have chosen this, because the standard model is renormalized. And usually there are two arguments in favor of renormalizability. One argument is that renormalizability is some kind of a principle. So when we construct the model in particle physics, this is kind of a principle which we choose, and we select renormalizable models, and we know how to deal with it. So in a sense, we're searching under the lamp. The other argument is that any theory in low energies is renormalizable. So if you go down and you introduce non-renormalizable interactions, usually the coupling has a negative mass dimension. So at low energies, they all are suppressed. And so looking at low energies, what is low energies dependent? Then only non-renormalizable can disappear, and in a sense, we are bounded for renormalizable interaction. But anyway, we know that people struggled with non-renormalizability for quite a long time. Weak interactions in the past were non-renormalizable. Massive gauge theories were non-renormalizable, and people always thought of a possibility still to deal with them. And after all, gravity is non-renormalizable, and this is probably one of the main puzzles. Of course, you may think that the way to construct quantum gravity is not related to field theory, maybe the string theory, maybe something else, but still, a kind of a dream was to build a model where you can work with. So that's why today, when unfortunately at the accelerators we don't see any new physics, people start looking back at gravity, looking back at non-renormalizable interactions in a sense of effective field theories and from the point of view of some ultraviolet existence of ultraviolet complete theory. So I will try to show you that the usual methods of quantum field theory, when applied to non-renormalizable theory, still work. So the problem is there, but still we can do a lot of things in non-renormalizable theories. with the methods of usual quantum field theory. Usually people discuss two main problems. One problem is the appearance of divergences of a nu and nu type, which create nu and nu operators which are divergent. And so we have infinite kind of arbitrariness in these fields. And this is the real problem. And of course, it's something which I cannot give you the answer to this problem or this recipe. But the other thing which people usually discuss on a more phenomenological level is that in non-renormalizable theories, the amplitudes increase with energy. So sooner or later you violate unitarity. So you remember when we considered weak interactions like for Fermi interaction, people said that there will be violation of unitarity when the energy reaches the value of inverse Fermi constant. So now we know with the help of the Higgs boson, this problem is not there. But anyway, so when you introduce non-renormalizable interactions, amplitudes start growing with energy and sooner or later violate unitarity. But this is happening in a pure perturbation theory. When you take some diagram in one loop, say, you calculate it, it grows with energy. So you don't know what happens if you add 2 loops, 3 loops, infinite number of loops, if you sum them up. Remember what is happening in the renormalizable theories. You have the amplitude, which increases with energy like a logarithm. So you take the logarithm squared, logarithm cubed, you take the so-called leading logarithm, and you sum them up, this leading logarithm, you sum them up usually downstairs in the geometrical progression, and you have asymptotic freedom. In fact, you would have increasing amplitude with energy, but logarithmic increase, very mild increase. But then you sum them up. You sum them up in an infinite series of diagrams. That's what you do in a usual renormalizable field. So in non-renormalizable case, instead of log, you have a power-like behavior. So the question is, can you sum them up and to see what happens afterwards? And this is exactly the question which I'm trying to address now. How to sum up the leading contributions with respect to the energy in all orders of perturbation theory? Can you do it the same way like you do it in the renormalizable case? In the renormalizable case, you use the renormalization group to sum them. So usually people say that the renormalization group comes from the renormalization procedure, which is a multiplicative. So you renormalize your theory, multiplying your green functions by some z factor. And this is a group operation, multiplication operation, so a simple group, which is the renormalization group. And so you write down the renormalization group equation, which reflect this property of multiplicative renormalizability. In fact, it's not necessary. In fact, you have it even in non-renormalizable case. I will try to show it. So the key ingredient here is locality. So you have a local quantum field theory, and from the requirement of locality, and with the help of Bogolyubov-Parasyuk theorem, you get local counterterms, and that gives you the equations, which are nothing more than the renormalization group equations, even in non-renormalizable case. So my talk is based on a sequence of papers written with my younger colleagues. So it's a long story already, and I will show you an example how it. So let me come back to a renormalization procedure. So you start with some Lagrangian, then you calculate your divergences, you introduce the counter terms, which will kill these divergences, and you have a finite answer. So these counter terms, in the usual case, can be reinterpreted like multiplication by some z factors. So you multiply your green function, which you calculate 2.4-point green function. You multiply it by some renormalization. You multiply them by some renormalization constant, which is equivalent to the introduction of these counter terms. This is the usual procedure, and this is exactly the renormalization constant which obey this group relation. And then to calculate this constant, you use a renormalization operation, which is, we call it Bogoliubov renormalization operation, but in the international literature, sometimes it's used BPHD renormalization operation to calculate this count. So you use this operation. So symbolically, it's written here. So 1 minus k extracts the singular part. Anyway, so it's just general formulas. And so when you do it, you first subtract these subgraphs. If you have some Feynman diagram, it's a graph. They have subgraphs. These subgraphs can be also divergent. So first you remove the subgraphs. And when you remove all the subgraphs, which is called incomplete R operation, R usually denoted by R prime. So first you subtract all subgraphs, and then you have final expression, which is divergent and which is local. And this is a statement of the Bogoliubov-Parasyuk theory. So after subtraction of subgraphs, the divergence is local. Local means that if you write it down in terms of the fields, it can contain just product of fields, and also it can contain several derivatives, but finite number of derivatives. Or in momentum space, some powers of momentum, some polynomials. It cannot contain log of momentum, only polynomials, or finite number of derivatives. That is a local field. So the statement of the theorem, independently whether it's renormalizable or non-renormalizable anyway, is that after subtraction of subdivergences on each step of perturbation theory, the expression is local. And this is a key statement. From this statement, you get everything.
Why is key?
Sorry?
Why is key that locality is so?
Because the statements come from this locality. In fact, we work with local field theory. I'm not talking about the string theory or something else. I'm just talking about local quantum field theory described by the Lagrangian, which is a function of fields and also contains finite number of derivatives, which is a typical situation we deal with.
Ой, Таня, ну а как я делать буду? Ну ты что?
So, what will be the difference in non-renormalizable case? In non-renormalizable case, when you subtract these divergences and you look at the counter terms which appear, which are local, but at each order of perturbation theory, you will have more and more derivatives. So it's still finite number of derivatives, but the number of derivatives will increase with the order of perturbation theory. In the renormalizable case, they do not increase. There's either zero number of derivatives, or say 1 or 2 derivatives, nothing more. Because this repeats the Lagrangian, and you start with the Lagrangian with finite number of derivatives. In non-renormalizable case, each order of perturbation theory will add you new and new derivatives. That is to compensate the dimension of the coupling constant. The coupling constant have a negative mass dimension, say 1 over m squared. The effective action is dimensional. So when you calculate contribution to effective action, when you have 1 over m squared, you have to compensate it with something. Then you think you have to compensate this momentum or in coordinate space derivative. So you have derivatives, more coupling constant you have, more derivatives you have. That is how it takes place. But nevertheless, this procedure of adding these new counter terms, even in non-renormalizable case, you can interpret like a multiplication procedure, but not precisely multiplication procedure. It's slightly different. I will explain you what is different. So you try to reinterpret it like in the renormalizable case, the addition of counter terms, like multiplication of the Green function of some constant. But now it will not be a constant, in fact, it will be some operator. What will be the structure of this operator? This operator will contain derivatives because the counter terms contain derivatives. So the z factor, if you interpret it this way, will also contain the derivatives. Derivatives in momentum space are momentum. So the coupling constant, the renormalization constant becomes a function of external momentum. polynomial. So because in each order of perturbation theory, you have finite number of derivatives, so you have a polynomial, so Z factor becomes a polynomial. When you multiply some Feynman diagram with this Z factor, which contains a polynomial, this polynomial is some momentum which is running through the diagram. So when the coupling was a constant, it's just simple multiplication. Now, if you multiply by a constant, which is momentum dependent, and momentum is running through the diagram, and you know in Feynman diagram, you integrate over momentum, which is running through the diagram. So this momentum, which is inside this Z factor, have to be integrated over the remaining diagram. So it's not a simple multiplication in a sense that you just multiply, but you multiply first, and then this momentum have to be integrated over. That is the complication. And when you do it, this momentum, sometimes inside the diagram, it can cancel some of the lines in the diagram. Because momentum is standing upstairs, propagator is 1 over p squared. So sometimes it can just cancel. So the diagram is slightly modified. That is some example from the gauge theory. And we calculated it in gauge theory, 8-dimensional gauge theory. And so this is a Z factor in one loop. This is G is a coupling constant. This coupling constant has dimension of a mass squared. To compensate this constant, we have S and T. S and T are Mandelstam variables. So I'm discussing some scattering amplitude, 2 by 2 scattering amplitude in a massless case. So the only variable are Mandelstam variable S, T, and U. So for a particular diagram, it depends on S and T. It's the product of S and T. So this is dimensionless combination. This epsilon is a divergence. We use dimensional regularization. So 1 over epsilon is ultraviolet divergence. And so usual Z factor in renormalizable theory will be G square over epsilon. But now since G square has negative dimension, it's compensated by momentum. So these momentum. So when you multiply one loop diagram by this Z factor, this S and T go inside this loop. You have to integrate them over. And they cancel some of the legs. And that's why multiplication gives you least proceeding. So in one case, T is canceled, in one case, S is canceled. So you see, it looks like multiplication, but it's strictly speaking more complicated operation. You have to integrate it all. So you can ask me whether we still have a group operation. Yes, we have, but not exactly. It's rather semi-group because the inverse operation is not clear. When you integrate momentum over, you cannot take it back, like in multiplication. So it's a kind of a semi-group. Still, it allows you to write down the equations. And this is a continuous group. Right.
So, one parameter, yeah?
No. Yes, I think it is one parameter.
Yeah, I think how you spell is one parameter.
Yes. There will be parameter. I will come now to this. Yes. So now let me try to describe you what happens if you take some amplitude as n loops. You calculate it. You calculate the divergent part of it, and in what follows, I will talk only about leading divergence. So in one loop, it's 1 over epsilon, where epsilon is the parameter of dimensional regularization. In two loops, you have 1 over epsilon square, which is a leading divergence, and 1 over epsilon, which is subleading divergence. So at the moment, I will ignore subleading. I just take the leading divergence. It's equivalent to consideration of leading log approximation. So that's what I will do in what follows. Leading log approximation, leading divergence. So my leading divergence is n loop is 1 over epsilon to the n. In dimensional regularization, to compensate the dimension, which is non-integer, you introduce some parameter. Usually this parameter is denoted by mu, right? So this is mu to the power n epsilon, and this is to compensate this dimension. And this is mu, it will be just the parameter which we're talking of a renormalization group. It's a continuous parameter. We will differentiate with respect to this parameter. This is expression of the calculation of the leading order, a leading contribution, but just calculation of the diagram. N is the number of loops, and this N corresponds to the power of x. In fact, these two numbers are equivalent because in N loops you have one of epsilon to the N. But then what you do, you subtract the divergences because you have to do the R operation. So first you subtract the one loop divergence, and N minus 1 is left. Right? So you take the one loop diagram, you shrink it to the point, you take this counter term, and what is left is N minus loop diagram. And this is the contribution of this diagram. You see, it's leading pole, so this is N, but this is N minus loop diagram. Then you continue. You go to 2 loop subgraph, 3 loop subgraph, until you come to the N minus 1 loop subgraph. And what is left is just one loop. And you have the whole infinite series of these terms. So starting from the diagram itself, this is subtraction of 1 loop subgraph, so on and so forth. And this is subtraction of N minus 1 loop subgraph. So the whole infinite series for the diagram. And now the statement of this locality of this Bogolyubov-Parasyuk theorem is that this expression has to be local. Let me remind you that when you have this formula written with the mu is a dimensionful parameter, dimension of a mass. That means that in order to have dimensionless expression, this mu have to be divided by some momentum. In fact, it's mu square over momentum square. And that means that when we are trying to expand it over epsilon, and if I have a log of mu, it means it's log of mu over momentum. And this is non-local, because log of momentum is non-local expression. Only polynomials are local. So the statement of a theory which tells you that the total expression is local means that all these log terms have to go away. They have to cancel. So all these terms together will have to cancel these terms of log to any power divided to epsilon any power. That should go away. So when you make this expansion, this term should disappear. I will show you now on the 2-loop example how it is. But that is the main statement. When you do it, that means that all these numbers have to be related somehow. Otherwise, this cancellation will not take place. And this has nothing to do with renormalizability because it's related to locality. So you have relation between all these quantities. And you have, for n quantities, you have n minus 1 equations. That means that you can solve this equation in favor of one of these numbers. So if you solve them in favor of this term, you have a relation. For instance, this leading term is related to this one by this simple formula. Let me remind you that this expression is a one loop diagram. So that means that the highest pole is always related to the one loop. That is something which people are familiar with in usually renormalizable case with the beta function. You have one loop beta function, you can calculate the leading term in any loop. That's exactly happens here. If you have one loop contribution, you can calculate all the leading poles. So it's always true. And that happens us to relate all these divergences. Let me show you an example how it works, because maybe it's a little bit difficult to digest. So let me show you first the renormalizable case. So suppose we took phi to the 4th theory, and we take this 2x2 scattering amplitude given by this Feynman diagram. So it's a 2-loop diagram. You calculate this diagram, and you have a leading pole and sub-leading pole. So I'm interested in the leading pole only. So 2 loops, second order pole, A to. Now then, you know that in this diagram, there is sub-diagram, this one. One loop sub-diagram, which is divergent. So you have to subtract. So what you do, R prime operation, you take the diagram itself, and you subtract the divergence of this one loop diagram. You shrink it to the point, and you get this diagram as a result. So you write it down. So this is the contribution of the diagram itself. This is the divergence of one loop path, this path, and this is what is left. And you see, this is one loop diagram. And this is one loop. And this is two. But the log have to cancel. You expand over epsilon. You have a log term. You have a log squared, another log from here. And these two logs must cancel. Otherwise, it will not be log. But this coefficient is a leading two-loop coefficient. And this is just the product of these two, one loop. So in order to get cancellation, we should have this relation. So A2 is A1 squared. So two-loop term, leading term is just the square of the one loop. And otherwise, they will not cancel. So exactly this happens if I take this theory in non-renormalizable case. I take 5 to the 4th in 6 dimensions, in 8 dimensions. It will be non-renormalizable. So everything will exactly the same, but the coupling will have negative dimension. This dimension will be compensated by powers of momentum. These powers of momentum will be sitting inside this loop, and they have to be integrated through the remaining loop. So this is operation of integration through. But otherwise, if you forget about it, it is just exactly the same. This two-loop contribution but it's not a square anymore, because now it's a product, and now you have to integrate it through. But still, it can be calculated through this integration from the one loop. So there's nothing new in the higher order pole. Everything is governed by one loop, and it always works, even in non-renormalizable cases. That means that you, without a real calculation of diagram, pure algebraic, you will be able to calculate all higher loops in any order. And if you calculate them in any order, you can try to sum them up.
Wouldn't you have more types of subdivergences?
Yes, I will have two different types of subdivergences. Some of them will contain the same number of legs, but more derivatives. But others will contain more legs. They will also be divergent.
Yes.
So that's true. But it so happens that when you try to trace what happens with the leading divergence, the terms with more legs will not be. So in fact, when you go further, you have more and more complicated, because you will not be able to restrict yourself, say, for the 4-leg amplitude. You will have 6-leg amplitude. So altogether, it grows up. So if I want to concentrate at the moment for the 2x2 scattering amplitude in the leading order, I don't need all that terms. They will not be involved in the game so far. So now I want to try to write down the relation. So this relation, which I considered before, this one, I want to try to write it down in a form of a recurrence relation. So I will try to relate n loop divergent with n minus one loop divergent to have some recurrence relation. And this, in fact, comes from this formula. So what you get when you subtract n minus loop divergence and you left with one loop live diagram, this line that you take, you start with 4x4 scattering. You do this R prime operation. It's very long expression, but I don't need all this expression. I just need the term of one loop, because I solved this equation in favor. So what can happen if you try to extract this one loop graph? This one loop graph can be standing at the edge of the diagram, or it can be somewhere inside the diagram. What else? For instance, you can see there 5 to the 4th theory. You take the bubble. This bubble can be to the left or to the right, or it can be inside. So both possibilities are possible. So, and then you can try to write it down formally in pictures. And that's what you see, that this is when this graph is tending to the left, and this graph is tending to the right, or this graph is tending in the middle. And all the rest is n minus 1 subtraction. So then if it is tending to the left, all the rest is n minus 1 loop. Or if it is tending to the right, this is n minus 1 loop. But if it's tending in the middle, so these two together have to give you n minus 1 loop, and you have to sum the overall possibilities. So anyway, this is a formal relation, but what you should have in mind that in case of renormalizable theory, these are just numbers. It's a divergent part, it's a number. And so it's multiplication procedure. If it's not renormalizable, this is not the number. This is the polynomial of a momentum. And this polynomial has to be integrated through this diagram. So it's no more simple multiplication, but still, this holds. So sometimes it can be slightly different because it depends what kind of theory you consider. In phi to the fourth theory, you have a quartic vertex in the Lagrangian. In a gauge theory, you have quartic and cubic vertex. So sometimes they are the diagrams, the one loop diagrams, they are not bubbles like here, but they are triangles. So this is another possibility, but it depends on the theory. In one theory, you have this, and the other theory, you have like that, but it doesn't matter. In fact, it's in any theory, you can see what you have. And by the way, in supersymmetric case, you will have only this kind of relation. In non-supersymmetric gauge theory, you have both. But this is more or less technical. So this is a kind of a recurrence relation, which relates n loop divergence with n minus 1 loop divergence. And I will show you how it looks like analytically. This is the recurrence relations we have in mind. This one is just written another way. Sorry. So this is n is the number of loops. This is the leading divergence in n loops. This is the leading divergence n minus 1 loops, and you have to integrate it through LS. So in fact, you can convert this recurrence relation into a renormalization group equation. So into differential equation. In a renormalizable case, you also have a recurrence relation, of course, but then you have a renormalization group equation, which allows you to solve. So in this case, to get the equation, you have to sum up. You have to sum up the leading terms, the sum factor, and this function will update the equation. And this is the renormalization group equation written here symbolically again. You see, this is this term integrated over triangle or over bubble, as I said, depends on the theory. And this is the second term, and this is nonlinear term, and this is integration over bubble. And d over dz here is just d over d log mu squared. So it's a usual renormalization group equation, which you have, and if you look at the renormalization group equation for the green function in say 5 to the 4th, exactly this renormalization group equation for the green function. Let me remind you that when you write it down for the coupling, you write it with the beta function, so the right-hand side of the beta function is the square of the coupling. And so this is then. So then this will be the total square. It's with integration here, so you cannot see it, but in the renormalizable case, integrals disappear, so it's the total square, 1 plus a squared. So this is a familiar form of a renormalization group equation, but in this case, it's more complicated. So we did this kind of exercises for several examples. So we considered the supersymmetric theory in dimensions 6, 8, and 10. So why supersymmetry? Why so complicated model? The motivation. Sorry, I have to. You know, N equal 4 supersymmetry happened to be a finite theory. So people thought that maybe if you look at the theory with maximal supersymmetry in any dimension, probably it has also very nice features which we do not quite understand. So the first example is take 6 dimension N equal 2 supersymmetry. Then 8 dimension N equal 1 supersymmetry. It's a maximal supersymmetry realized for this when you restrict your spin to 1. And so indeed a lot of cancellations take place, but not all. So in N equal 4, indeed in 4 dimensions, all divergences cancel. In 6 dimensions, we will see it soon, they do not cancel. Many of them cancel, but not all. But anyway, we made these kind of exercises for maximally supersymmetric theories in 6, 8, and 10 dimensions. Then we played the same game in 5 to the 4th in D dimensions, with D is a higher level. Then another example was a pure gauge theory in D dimensions. And then the last one in supersymmetric Wess-Zumina model, but not 5 to cube, but 5 to the 4th. Why was it interesting? Because in supersymmetric theories, we have so-called non-renormalization theory. And one of the theorems says that superpotential is not renormalized for the reason that all relative corrections are the integrals over the full superspace. And superpotential is the integral over chiral part of the superspace. And so the statement of the non-renormalization theorem was that chiral parts are not renormalized. In fact, we found out that this is only true in a renormalizable case. In non-renormalizable case, the chiral part is renormalized. So find out how it became, maybe I'll show later. Okay, so our aim is to approach somehow the gravity theory, but that happened not to be so easy as you can imagine. Right, so example of 5 to the 4th theory in D dimensions. So this is the 4-point scattering amplitude depending on Mandelstam variables in S, T, and U channel. As usual, they're related to each other. So you have a power series. These are Feynman diagrams which you have. So it's 1 loop, 2 loops. So you have to subtract subgraphs. These are the subgraphs, the usual procedure in 5 to the 4th, very well known. But now we look at these diagrams when you integrate over 4 dimensions, 6 dimensions, 8 dimensions, and so on. This is the recurrence relations I was talking about, but now it's analytic form. So you look at this analytic form, which corresponds to this picture. And you have integrals here. What are the integrals? Yeah, when you calculate this counter term, it depends on momentum. So if momentum have to be integrated through the 1 loop diagram. This integration can be made in general form, introducing Feynman parameters. Then you integrate over momentum, but you have integral over Feynman parameters, and what is inside depends on this Feynman parameter. So what is shown here is exactly that. This X is the Feynman parameter which you introduce for this 1 loop diagram. And so it stands here. So power of D is dimension. So when D equal to 4, you have D over 2 minus 2 is 0. So it drops. Yeah. Now, in the case of renormalizable theory, these functions, they do not depend on this ST and U because they are constants. So the integral also drops. And so you have pure algebraic relation relating the N loop divergence. S means S channel. T means T channel, U means U channel because you have 3 channels, they all relate. The full amplitude is the sum of the 3 channels. So in a renormalizable case, the integral drops, this dependence drops, and you have an algebraic relation, which is just gives you simple geometrical progression, nothing. But in non-renormalizable case, D greater than 2, then 4. So these are polynomials. So you have to integrate them through. Formally, you can integrate and then you introduce, you see, T prime and U prime, they depends on this X. So this Feynman parameter goes inside. But these are polynomials, they trivially integrated, of course. So in each particular order of perturbation theory, all integrals drops, you have again algebraic relation. But only in each particular order of perturbation theory, because in general, it's integral relation. So this relation allows you, starting from one loop, calculate all the leading divergences in any loop in any dimension, which are polynomials, which are no more constants. But this relation allows you to calculate everything algebraic. So it works. We checked it on the diagram, just calculating the diagram and comparing with this. Now, you can sum them up to get equation. So if you sum them up, multiplying by some factor, is summing up from 2 to infinity, you have this equation now, d over dz, of this gamma. Gamma s is S channel. So you have gamma s, gamma t, gamma u inside. But this is again integral relation because they depend on momentum. If we go to d equal 4, all momentum disappears, all integral disappears, you have a usual renormalization group equation. I will come to it a little bit later. But in general, for any dimension, this is the equation. This is d over d log of mu. And so this is looking a bit complicated, but it's how it is. I mean, I cannot avoid it. You have to integrate this complicated thing, and these multiple sums appear because you have to integrate momenta, multiple momenta when you integrate over dp. You have this Gini factor. So it's quite complicated, but it's true. And this is how it looks like in any dimension. Now, particular case d equal 4, everything simplifies. I will show you in a minute. Now, let me give you an example of a gauge theory. And for this example, I will consider supersymmetric gauge. The advantage is that in supersymmetric gauge theory, a lot of cancellations take place. And if you consider 2 by 2 scattering amplitude, and you show the Feynman diagrams, these Feynman diagrams, after all contraction of all these momenta, all these indices which are there, everything is reduced to a sequence of scalar master integrals, which you have to calculate if you want to calculate 2 by 2 scale. And these scalar integrals are shown here. So it's A4 means 2 by 2 scattering, 4 leg. They have some 3-level expression which factorizes, and you have a sequence of diagrams. And these diagrams are shown here. These are scalar integrals. So all vector indices, everything, ghosts, whatever you have already there. And this is just master integrals. So in one loop, you have just a box. The advantage of supersymmetry is that bubbles and triangles exactly disappear in any order. So you have just a box. In 2 loops, you have 2 boxes, S channel, P channel. In 3 loops, you have also boxes, but you also have some diagrams, which usually called half tennis court diagrams. And it has some derivatives. These are some derivatives. So in general, you do not have just boxes. You have also some derivatives inside, so numeric. But anyway, so this is expansion. And you see the number of these diagrams is not very big. In fact, in the usual Yang-Mills, you immediately have thousands of diagrams. But in supersymmetry, they disappear and they cancel. And so this is the number. Of course, it's increases. But anyway. And you can try now to apply this same procedure here to calculate the leading divergence. So, by the way, this shows you why n equals 4 in d equals 4 has no divergence, because the boxes in 4 dimensions, all of them are finite. And so if you put d equals 4, you'll have no divergences at all. If you put d equals 6, you find out that this is still convergent, and these are convergent. So the first divergent diagram in d equals 6 is this tennis court. So in d equals 6, divergences start from 3 loops. This is a kind of byproduct of our analysis. In 8 dimensions, everything starts already from 1 loop, and there is no cancellation of ultraviolet divergence. So the dream that with maximal supersymmetry, you probably will have absence divergences in higher dimensions. No, it doesn't work. Anyway, so this is quite a universal situation for any loop. This expansion does depend on D. And we tried to apply this, our procedure to this kind of diagrams. And we found out that you can do it. And these are recurrence relations, which you get already written in analytical form. And you see this one is in 6 dimensions, n equal to supersymmetry. So bubbles and triangles cancel. And everything starts from 3 loops. And you have to integrate over triangle, because when you shrink diagram, what is left is triangle, not the bubble. That's why since this triangle, there are 2 Feynman parameters. Because for triangle, you have to introduce 2 Feynman parameters. So this is 2 Feynman parameters. And this relation happens to be linear. So nonlinear terms also cancel because boxes cancel. So in 6 dimensions, the equation look pretty good. And there were big temptation to try to find out the solution. But we didn't find it. I will show you equation in a minute, but we didn't find analytical solution. We did only. But anyway, this is the equation. This is the recurrence relation, which relates n loop in n minus 1. Then we convert it into renormalization group. So in 8 dimensions, with n equal 1 supersymmetry, this nonlinear terms do not cancel. So the full relation is here. Again, these are Feynman parameters here. And these are Feynman parameters for the bubble, because when you shrink from both sides, you have a bubble. So this is more general expression. And these are recurrence relations. And we checked it to many loops so that all calculation of diagrams explicitly exactly fit into this. But now you can calculate the leading divergence of just substituting one loop here and generate all. If you convert them into equation, then in 6 loops, you have a linear, in 6 dimensions, you have a linear equation. So this is the equation. So it's a linear integral differential equation, which I don't know how to solve. So I spoke to mathematicians, and I don't know. Looks not very complicated, but we failed to find a solution. In 8 dimensions, it's non-linear. It's already much more tricky. But in some particular cases, you can solve this, and I will show you. Now, the Verzumina. So Verzumina model, this is the usual Verzumina model, but phi to the 4th instead of phi cubed. The typical, what is called Verzumina model is phi cubed. But this is when superpotential is phi to the 4th. And the coupling has dimension 1 over mass. And then we looked for radiative corrections, and we found out that you do have radiative corrections to the chiral part of the effective function. And so there are 2 types of 4-point functions. They are pure chiral one, or anti-chiral one, and the mixed one. And both of them have divergent radiative corrections in certain number of loops. And doing all this procedure, which I was trying to describe you get the renormalization group equations, which are written here for the chiral part. S means again S channel, P channel, U channel. And this is the mixed part, and these are the equations. There are some symbols here. And this is, of course, related to all these Feynman parameters. So X is a Feynman parameter. So bit tricky. But these are equations which you get. And you can calculate all the leading divergences, and you can even try to solve. I will show you in particular case how you can solve. So now, already about the symbolic here. Phi to the 4th. So if you take d equals 4, so everything, all the integrals, everything disappears, and the equation looks, has this form, where lambda is the coupling, and you can solve it, of course, and this is the solution. So we have a geometrical progression, very well known, and you see. So you see here 3 over 2 is a beta function, and when energy increases, log becomes negative, and this is lambda over 4. So no surprise, so our solution just reproduced what we expect. But now you can say, what if d not equals 4, but 6 or 10, can we still solve this? So it's integral differential equation. But I claim that in a sense, symbolically you still can solve. And when you solve it, you have a solution which looks like geometrical progression, but there is some symbol which comes from when you try to expand the perturbation theory. Finally, you have one loop diagram, and then you have two loop diagram, and you have to calculate one loop diagram through two loop diagram, all this procedure. So this symbol somehow reflects the fact that this procedure is a bit tricky. So when you expand it in perturbation theory with this symbol, this is rather tricky operation. So symbolically, you can write it down. I even don't know whether mathematicians have such a symbol. So probably yes, probably no, but anyway. But the point is that probably you can analyze the behavior of this function inside this symbol. And then you can say some words about high energy behavior of this amplitude, even in higher dimensions. And this analysis tells you that you still have Landau poles because the log becomes negative. And this combination of ST and U is always positive. That means that you have Landau pole in any dimension. High to the fourth and D dimensions in the leading order. So, not very good for phi to the fourth theory, but anyway. Now, you was about the gauge. In a gauge case, it's very difficult to solve this equation. But for the particular sequence of diagrams, you can solve it and look at it and have some impression of what is the behavior of the function. So if you look at the so-called ladder type diagrams, so in 6 dimensions, the first divergence comes from the tennis court diagram. So pure boxes do not diverge. So when you have a divergence, you should have this tennis court somewhere inside, and then you can add this ladder. So let's consider this sequence of diagrams. And for this sequence of diagrams, surprisingly, you can solve this equation. And this is a solution. So this is the solution of this equation in this sequence of diagrams. And you see they have exponents. So it's an S channel. S is positive. And so this amplitude will increase. While in T channel, it will decrease because T is negative. So you see that the solution, is whether you have a T channel or S channel diagram, depends on the sign. So you do not have a situation when from all channels, all the amplitudes decrease. Some of them increase with energy, some of them decrease with energy. So whether it's good or not, probably bad. But anyway, this is the situation. So that is what is happening in leading order. But in fact, you can go further. You can continue this analysis in the subleading order for subleading logs. And then you have also complicated equation. But again, for the ladder diagrams, you can solve. And then this is the solution for the ladder diagrams. And again, you have the Z in exponent and the same situation. In fact, subleading diagrams more or less follow the pattern of the leading. Subleading log follow the pattern of leading. Now, in 4 dimensions, in 8 dimensions, you have boxes which are divergent already, and you can have this ladder type diagram, purely ladder type. And again, equation is integrally differential and non-linear, and so no way. But for the ladder diagrams, you can solve. And the solution, so for the ladder diagram, it's a pure differential equations. Integrations go away because the ladder doesn't depend on T and S. It depends on T and U. It depends only on S. So you can write down equation in this form, and this is not a total square, but it can be solved, and this is the solution. And you find out that in this solution, you have infinite number of Landau poles. Whether you go in D channel, in the S channel, you have infinite number of Landau poles, which probably reflects the fact how it is in general, because we try to solve full equation by numerical methods. And this numerical method more or less confirm the existence of these poles. So probably this particular chain of diagrams somehow reflects the general feature of solution. So it's an infinite number of Landau poles. In fact, analyzing this situation in general, you can have only 3 possibilities. So either you have one Landau pole, or you have infinite number of Landau poles, or you have exponent-like solution. So from the point of view of high energy behavior, it looks like that because ST and U have different sign, you probably do not have a regime when all amplitudes decrease. Always something increases. And I think this is more or less general situation. Now, I come to my conclusion. So ultraviolet divergences in non-renormalizable theories are local. It can be removed by local counterterm. This is more or less statement of the Bogolyubov-Parasyuk theory. So the main difference is that the Z factors, if you try to remove divergences with the Z factors, these Z factors, they depend on momenta, like polynomials of momenta, and they are not a constant anymore. So simple multiplication is removed by this operation which I tried. Now, based on locality and the theorem, you can find out that the higher order divergences are always related to the lowest order. So you can write down the recurrence relation, which allow you calculate the leading divergences starting from one loop in an algebraic way, even in non-renormalized. Now, these recurrence relations can be easily converted into equations, which I will call generalized renormalization group equations, but they have not simple differential form, but they have integral differential form with the integration over these finite parameters. One possibility to remove this integration is, say, consider the partial, you know, when you have S, T, and U. T and U depends on angle. In a framework, center of mass framework, say S equal energy squared, T equal energy squared minus 1 plus cosine theta, and U 1 minus cosine. So you expand over theta. This is the like a partial what is it called?
Wave.
Partial
wave.
So like expansion of partial waves. Then you fix the particular partial wave, you fix cosine power of cosine theta, and then in this equation you can integrate it all. So for partial waves, you can convert the equations into pure differential form. I don't know whether it's useful or not, because it will just for particular partial. Maybe, but I don't know. Anyway, but in general, it's integral differential. So these equations, in fact, allow you to sum up the infinite number of leading diagrams. They're summed in a way that you have to solve this equation. But sometimes you can solve them analytically. For particular example, I do it. Otherwise, you can solve them numerically. And this numerical solution, you can look how it behaves for high energy. So this way, you can treat the scattering amplitudes from the point of view of high energy behavior. So all equations in any theory, they're more or less similar. Like we considered scalar case, we considered gauge theories, and more or less the same, though technicalities are different. And in fact, pure Yang-Mills in D dimensions is rather tricky. It's more tricky than the supersymmetric because of no cancellations, and you have bubbles, triangles, everything together. So it's rather tricky, though the general methods, I think it doesn't matter which theory you take. So I would like to apply it for gravity, and that will be our next step. Okay, so that's it. Thank you very much.
Thank you for excellent presentation. So if you have questions.
Mày muốn tức là nó bán sầu bán lắm tuổi lúc đây đợi
I mean, it means that all these infinite counter terms now are dependent.
And you know, I somehow omitted that you have to subtract this. So what we did, we used minimal subtraction scheme that way fixing all the arbitrariness in a minimal way. And the leading divergences do not depend on this arbitrariness. So in a sense, the fact that I consider the leading divergences only justifies the use of this minimal subtraction scheme because they do not depend on the scheme. But in fact, in general, you look at the theory, which is non-renormalizable, you have infinite arbitraries, which have to be fixed somehow. And we know that since it's an infinite arbitrary, so there is no way that to fix something in one loop, then in two loops, then in three loops. The counter terms will increase and increase, so more derivatives, more legs, more everything, and your theory is not defined. And this is the problem, which I didn't address. So as I said, there are two main obstacles, and one of them is this infinite arbitrariness, and the other one was the violation of unitarity. So I addressed the second part of this problem, not the first. With the first one, I understand that it is not that simple. I mean, I can give you the rest. My guess is that if you still try to do something like this, you have to have in mind that probably not a constant have to be fixed, but some function have to be fixed. So infinite arbitrariness somehow hidden inside not a fixation of a coupling constant like one number, but fixation of some function. But here I can just speculate.
What is the flow?
Sorry?
What is the meaning of the flow? You don't have a normalization. So what is the meaning of this flow?
As I said, if you consider the scattering amplitude, it depends on momentum. And I know how it depends on momentum. So I can trace it, I can calculate it, I can sum them up. I can try to see how whether this amplitude decreases with energy or increases with energy. I can do it despite the fact that all this arbitrariness is not fixed. So it's not a complete solution of the problem, but at least partial.
Does it make sense to look for fixed points of this equation?
You know, since I do not quite know how to solve them, so I will wonder if there is a fixed point. But this I don't know. But that would be interesting to get it, of course. But I'm not sure.
Nghệ thuật còn sự im lặng.
That's why have to find out how to solve this. Of course, we would prefer analytical, something analytical, right, rather than numerics.
How this problem will develop?
First, we started calculating Feynman diagrams, and then trying to use our operation, not really calculate the integral, but this way. But instead of calculating this integral itself, we did our operation and take in one loop, and then we realized that what we do is just this procedure. We write it down. But first, we calculated a lot of diagrams that we have a material the playground.
Concerning the example of Bessel-Minot in 4-dimension,
yes,
there was a paper in the 90s of Losset, Nekrasov, New, Chetashvili, and is it the same type of model? It was called then 4-dimensional avatar of 2-dimensional.
Well, I'm not sure that we are addressing the same question or even the same model. I don't know exactly what is there, but here it's rather attempt to see what happens if you just change the superpotential. And the main statement is if you change the superpotential, or you put arbitrary superpotential with the higher powers of momentum, of the field, then the chiral part of effective action will get radical correction. And the reason for this is this dimension component, because the coupling has a negative dimension. To compensate it, you have additional derivatives which convert the full superspace integral into the chiral, into the chiral superspace. So this happens if you have negative dimensions. So you need the scale to compensate this additional covariance.
actually rather simple. You just see that you have additional derivative. But we didn't realize that it's not exactly the superpotential get find infinite corrections. It's the chiral part of effective action, because additional derivatives means that you have not a, by definition, let's say superpotential without the limit of the rest and derivative in effective action. So you have corrections with derivative, but chiral part. And I'm not sure whether they address the same question, or maybe not.
Nó cứ kể những cái chuyện như là tiền đấy là nghe.
There is some new development in this Vesumino.
Cứ chuyện những cái chuyện mà kiểu như là
Paper by getting Costello this week coming 95 pages. Can do something twistor methods and so on. So it's a model which arises new interest. I was thinking whether you can say something.
I will have a look, but what I told you about this, will it be in archive next week? It's quite fresh.
I think otherwise, I think the debug which you actually named, but I don't know if it's clear. So what comes out, the nuance you didn't, you leave it aside, is that many part functions have new type of divergences, which require new arbitrage.
You know, once if we take a 5 to the 4th model like example, but in 5 dimensions. So you start calculating for loop diagrams, right? You have more and more derivatives. Then you look at the 6 leg diagram. You find out that sooner or later, with the addition of loops, you will also start to be divergent. So you introduce the counter term, which 6 field, and trying to interpret it like with the C factors. I would say that C factors become not only functions of momentum, but also functions of the field. So these factors, these C factors start, they're expanded over the coupling constant. Coupling constant has negative dimensions. It's compensated either by momentum, then will be 4 fields, or by the fields, because fields also have dimensions. So this Z factor becomes a kind of a matrix in the fields and momentum. So everything becomes more and more complicated. Yes, that's how it is. But in the leading order, sometimes they separate.
So we have this nice and stable differential questions. Are you sure that the solution is
thằng số kia cũng nói cho ai nữa? Alexander.
We know that perturbatively they should have a solution, because if we substitute each other perturbation theory, perturbatively it should work. So I think that tells you that it should be a solution. What kind of a solution with which singularities in? My guess is that there are 3 possible singularities, as I said, exponential growth to decrease, 1 pole, or infinite number of poles. I think it's more or less general statement for this solution. It depends on whether the right-hand side equals 0 or not. It's like beta function 0 means a fixed point. Right? Here it's similar to that. That tells you how many poles you have there. So this kind of general analysis, but I cannot prove them like a mathematician. You know, I'm more or less on the physical level of rigorousness. But like a mathematician, they will probably kill me for this reason.
Any other questions?
Do you expect that the renormalization procedure of applied to gravity will depend on the dimension of space?
Yeah, of course it will depend.
Of course, but if you choose 2 and 3, and then maybe in some hard dimension.
You know, my analysis was related to existence to ultraviolet divergence. If you go down with the dimension and if there are no divergence, then there is no point yet to have this relation. That's why, so I'm not talking about lower dimension theories. I'm talking about the divergences of the laws in higher dimensions.
Yeah, that's why you can For example, you can
Bác gạo, bác ấy nụ cười còn có bao giờ cũng rất là thành công.
In 4 dimensions would be enough.
That's why I have to expect that there will be some dependence if you go 5, 6, and so on.
Well, I don't know. I know only that today many people start looking at all this. And in particular, after success of n-equal force intensivity with amplitude, with factorization properties, and all that, the same people who did it, Dixon, Bern, and others, they considered gravity. They use this formalism of formalism for the gauge fields. And they considered gravity also in this formalism. And they found out that this expansion over these boxes, which I showed in gauge theory, the same happens in gravity, but numerators are different. So this works also with different numerators. Probably this is the way to treat gravity with the help of this formalism, which is rather compact. But anyway, it's
số kỷ lục. Dùng những từ đấy nhiều khi chỉ dạng mấy chục.
I should ask one. Yeah. Does your approach applies to higher spin?
Well, we didn't try. We didn't try.
Because there somehow gravity appears almost
spin 2. Yes. Yeah. Well, I don't know. We didn't try. We tried several examples, you see. So I think that's the key point, as I said, is locality. If you have a local theory, and then that should work. But with high spins, you probably introducing high spin, you will not stop at a fixed spin. You will have higher and higher spins. Yeah, and that will be even worse than what.
Mình nói hay hơn nhưng mình không nói freely được.
Let's thank again. Мы надеемся, что еще будет у нас.
Приглашайте. А я вас приглашаю давно. Все, внимание.
Ну, прекрасно.
Конечно, я вас помню. Приезжайте опять.
Đã hiểu được cái con virus có được mà.